Okay, hey guys, we're going to be doing more maths today, more FP2 AQA. Get Jan12 out in front of you, please, and turn to question 4. That's what I'm going to be talking about. An induction question, but an induction question with a sequence that has been iteratively defined. So you get two different types of induction questions. One where you have to prove a formula, and then one like this one, where you have a sequence that's iteratively defined, and then you've got to prove its definition of something else. So if I write down what we have then, we're told, this is question 4 from Jan12, told that the first term in a sequence is 3/4, and that the sequence is iteratively defined, so the next term is equal to 3/4 minus the current term. So un+1 is the next term, un is the current term. And what we want to do is prove that this iterative definition is equal to just a regular old definition, that the nth term is equal to 3 to the power n plus 1 minus 3 over 3 to the power of n plus 1 minus 1. So I've done a video on iteration before. I'm not going to go into the whole principle of it, but we have to find the base case, assume that it works for some n equals k, and then prove it works for some n equals k plus 1. So let's start off then with the base case. It's always good to write down what you're doing with iteration. So the base case, we always have to think, are we going to start off from n equals 0 or n equals 1? Maybe some other number, but I've never seen that before. So in the question it says, prove by induction that for all n greater or equal to 1. So the lowest that n can be, your base case is n is equal to 1. So if we now have to prove that this definition is equal to this definition when n equals 1. So I'll do the left-hand one first. u2 is equal to 3/4 minus u1. So that's using the iterative definition there with n is equal to 1. And that is equal to 3/4 minus 3/4, because the first term is 3/4. Let's simplify that fraction, let's make it look nice. 4 is 16/4. So 16/4 minus 3/4 gives us 13/4. And when we divide by a fraction, it's the same as multiplying by that fraction upside down. So we multiply by 4 to give us 12, and we divide by 13. So the second term is 12/13, and I'm now going to prove that that equals this when n equals 1. No, yeah. Yeah, I've made this a little bit more complicated than it needs to be. This will work if you put n equals 2 into this now. You will get this because I just did it 10 minutes ago. But it's easier than this actually, and I'm not starting the video again. Instead of putting n equals 1 into here and working out what u2 is, let's put n equals 1 into here and work out what the first term is. Oh, I've lost my pen lid. Oh, it's all going wrong. I'll use this one. Right. So, starting again then. The first term using this formula here, u1 is equal to 3 to the power of 1 plus 1, so 3 to the power 2 minus 3 over 3 to the power 2 minus 1. 3 squared is 9, minus 3 is 6. So you've got 6/8, which is equal to 3/4, which is what we expected the first term should be. So that's our base case. Now, we're going to assume that for some n equals k, that this works. So, and then, like I said, write down what you're doing. This time, we're assuming, so assume that n equals k, that this works. What does that mean for it to work? That means that this formula is true. So I'm going to write down what we're assuming. We're assuming that the kth term, uk, is equal to 3 to the k plus 1 minus 3 over 3 to the k plus 1 minus 1. What I'm also going to do, and maybe off to the side of my page now, is write down where we want to get to, what we want to show. We want to show that this works for the k plus 1th term. So what does that mean? So we want to show, WTS, that u k plus 1, the k plus 1 term, is 3 to the power k plus 2 minus 3 over 3 to the power k plus 2 minus 1. That's what we want to get to using this formula here and the inductive hypothesis, which is what we've assumed. So let's have a go at doing that now then. So using this formula, uk plus 1 is equal to 3 over 4 minus uk. And now, by the inductive hypothesis, if you were doing this line by line, which is how you should always lay your work out, I don't have a big page that I can keep on going down. If you're doing this line by line, I would now write by inductive hypothesis. So by inductive hypothesis, we're going to swap UK for what we assumed it was earlier. And that's what the inductive hypothesis is, using your assumption. Right, so 3 here. So 3 over 4 minus UK, which we've assumed to be 3 to the k plus 1 minus 3 over 3 to the k plus 1 minus 1. When I was doing this earlier, I missed out the bracket, bit of a rookie mistake there, and things went wrong for me. But now I've got the bracket, I'm going to remember the double negative, which is where I went wrong. So two different ways we could do this now. We can make the bottom one whole fraction, and then dividing by a fraction is the same as multiplying by the the upside down of it. We could do that, but 4 doesn't really make a fraction nice with 3 to the power k plus 1. So what I'm going to do is get rid of this fraction here by multiplying everything by 3 to the k plus 1 minus 1. And that will get rid of the denominator here. So this equals, I think you'll be able to see that, this equals 3 times, you see that? 3 times 3 times 3 to the k plus 1 minus 1 over 4 times 3 to the k plus 1 minus 1 minus, in brackets, 3 to the k plus 1 minus 3. And we've got to get that to look like our want to show up here. First thing I'm going to do is expand the top and the bottom. So on the top, 3 to the power 1 times 3 to the power k plus 1. When you multiply numbers with the same base, you add the powers. So that gives us 3 to the k plus 2. 3 times minus 1 is minus 3. So far you can see we've got the numerator. We're not going to change the numerator now because that's what we want our answer to be. We just have to work on the denominator now. And that's all over. I'm going to use a dot notation for times. 4 times 3 to the k plus 1 minus 4. And now this is where the bracket comes in. Minus 3 to the k plus 1 plus 3. And let's tidy up that the bottom of this. One easy thing we can do, I'm not going to do a new line for this, minus 4 plus 3 is minus 1. So we've got our minus 1, brilliant, which means this, and you might be able to see how it's going to work now, this is 3 to the power k plus 2, apparently. How do they get that? Well, one thing we can do, remember, if you don't know what to do, do the only thing you can do. One thing we can do is factorise out this 3 to the power k plus 1. So let's do that. So we've got 3 to the power k plus 2 minus 3 over 3 to the power k plus 1. That's 4 lots of it, minus 1 lot of it, and then we've still got that minus 1. Okay, so you should all be able to see what's going to happen now. Four minus 1 is 3. And again, when we multiply, we add the powers. So 3 to the k plus 2 minus 3 over 3 to the k plus 2 minus 1. As required, that's what we wanted. That's what we wrote down we wanted to show. Cool. 6 marks. Nice one. Not too bad. What can I say? Here. What have we learned? It's a bit of a bad start, wasn't it, this video? What did we learn? I think we learned something. That bit was nice when I multiplied through the denominator of the fraction instead of making the whole thing one fraction, but you know, either way would have worked. So yeah, alright, cool.